All right, so we take aldehyde ketone, react with ethylene glycol to form a cyclic acetal. We use cyclic acetal as a protecting group. This is an ether bond. Okay, let's take a look. So it's just like acetal formation, nothing different. Okay, but this molecule contains two alcohols. Use as a small amount of acid as a catalyst, you get to a cyclic acetal. Okay, use as a protecting group, remove water, and to form this ether bond. And this ether bond is stable under basic condition, like a Grignard reaction, lithium aluminum hydride, sodium borohydride. They are stable in those conditions. Okay, if you want to remove, well, just like that's a property of protecting group, right? You can put it on, you can take it off like a hat. Okay, so if you want to remove it, flood them out with water. The product, the ketone form, the starting material, and the product cyclic acetal, they are in equilibrium. Okay, if you add a bunch of this, it's a Le Chatelier's principle. Add a bunch of ethylene glycol, drive equilibrium forward, you get to the product, the protecting group. If you want to get it out, add water to flood this out. We can go backward. All right. So here's how we use it. Okay. All right. Let's do this. Look at this synthesis. Ignore the ketone for now. Just focus on a double bond to a single bond. If we have just a double bond to a single bond, I think you know what reagent that is. Hydrogenation. Remember that? We just use catalytic hydrogenation. Okay. But now, when we have in the presence of that ketone, you can't do that directly. Otherwise, this ketone will get affected as well. Okay, so we're gonna protect the ketone by doing put the ethylene glycol on it first. Okay, and then followed by the functionalization. Do whatever you want as long as you don't add an acid. This guy will stay. All right, so do functionalization, and then remove the protecting group. Add water, add acid, flood them out. That's the product. That's how it works. Okay, one more example. We got one more example. Okay, so all right, very similar. This one we going from an ester to an alcohol. What reagent is that? This one. This one's a little. Okay, it's been a while since we talked about it. So we use lithium aluminum hydride. React twice on an ester from an alcohol, and don't forget quenching. All right, and but in the presence of that ketone, well, it's gonna get affected as well. So what do? Of course, protection. Okay, put the ethylene glycol on it first. Look like that. All right, and then you do functionalization. Do whatever you want as long as you don't add an acid. Okay, now we have an acid right here, so that might cause this guy to leave. But this is a second step. Use lithium aluminum hydride first. Add on to it, convert to alcohol, and then that's pretty much it. Okay, and then don't forget to flood this guy out. Add a bunch of water. Okay, and an acid. Deep protection. Yep, that's how it works. Okay. All right. On a side note, so the for acetal formation, I think you remember that ketone aldehyde react with two molecules of alcohol to get to acetal. Hemiacetal is difficult to isolate. Okay, but in nature, we actually have some cyclic hemiacetal that is stable. So it looks something like this. So we have a ketone and the alcohol in the same molecule, and they form a cyclic system like that because cyclic hemiacetal. Okay, and you will see this if you take biochemistry in the future. You have seen this before, but you just don't know. Okay, glucose and or sugar family, or the aldose family, ketose family. This OH attack right there from a cyclic hemiacetal, and this guy actually is stable. This is the primary form of the aldose molecule, aldose sugar. Okay. All right, that's it. So that's the user protecting group. Okay, let's move on to reaction number 3.